In previous class, we have seen in detail about Latimer diagram, and we also saw that the main purpose of the Latimer diagram was we get the E cell value for every step. And we also found that if we wanted to find the E cell of any step which is not directly related, in that case we should definitely proceed through delta G, because E was an intensive property which could not be added. So we had to proceed through the extensive property which is associated with that, that is delta G. So we have already done some few problems regarding the topic. Anyway, let's do one more problem on that. And let's start the class with the problem. So the question is, calculate E0 for the process Cu plus electron giving Cu using the following E0 values. And they have given copper 2 plus converting into copper plus, and also copper 2 plus converting into copper. So the E0 values for both these reactions are given, and we are asked to find the E0 for a particular reaction. So when questions come like this, the first thing you have to do is try to add the given equations and form the equation that we're asked to find the E0 for. Okay, so let's see how it's that possible. So for the equation required, it's actually Cu plus electron giving Cu. To form this, we need Cu plus on the left hand side and Cu on the right hand side. So where is Cu plus in the given two equations, or for the equations whose E0 is known? Cu plus is on the RHS for first equation. If we want it on the LHS, then we have to reverse equation number 1. First of all, let's name this equation 1 and 2. This is the required equation. To get the required equation, one thing we found now is we have to reverse equation 1 because we need Cu plus on the LHS. So if you reverse equation 1, you will get Cu plus on LHS. So reverse equation 1. Let's try writing that. So we have Cu plus giving Cu2 plus electron. And what will be the change in the E0 value? Since we have reversed it, E0 value should be just the opposite. That means the negative value of the given value. That will be minus 0.153 volt. Now we need copper on the right hand side. If you look at the second equation, we have copper which is in zero oxidation state on RHS itself. So we can write that equation directly. So we are just writing the second equation directly. And you will have Cu2 plus 2 electron giving Cu. What will be the E0 value? Because we have done no change to the equation, E0 will be as it is. So 0.341 volt. Now let's try to add both of these equations and see whether we are getting the required equation. So we have electrons, one electron on both sides will be cut. So here there will be only one electron left. Cu2 plus common on both sides. So what is left? We have Cu plus an electron which is pending here, plus an electron giving Cu. So if you compare the required equation and this one, they are both the same, which means we have used the two given equations to get the required equation. Now what will be the E0 value for this particular reaction? We can represent it as E3. Can we simply add the E0 values? The answer is no, because we have learned yesterday E0 was intensive and we cannot add it. So to find the E0 value, we have to proceed through delta G as I have told before. So we need to find delta G value for each of these steps. So for step 1, we will find delta G1, and that will be delta G1 will be minus NF E01. And as I have told, I am not going to substitute the value for F here because eventually that will be cut or cancelled out. So the number of electrons involved in the first equation is, you can see there is only one electron, so N is equal to 1 into F into, what is E01? Don't be confused with the two E01 values. Here you can see a plus value, here you can see a minus value. So there is a slight confusion which value to be taken, but always remember what is the equation you used to get the required equation. That particular equation's E0 should be taken. Okay, so in here we have reversed equation 1 to get the required equation. So you have to use the second value of E01. That will be minus value. So minus 0.153 volt. Now if you multiply them, you will have two negative signs. Let's cancel them. So in here you have 0.153 into F. This is delta G1. Now let's find delta G2. Delta G2 will be minus NF E02. Just like what we did before. Minus, what is the number of electrons involved here? Second equation you can see it is Cu2 plus 2 electrons. So number of electrons involved is 2 into F into, what is E02? There is no confusion regarding E02 because we just took the equation 2 as it is. So it is 0.341 volt. Now if you multiply them, you will have a negative value, and 2 into 0.341 will give 0.682 volt. There should be an F here. F, not volt. Delta G2 is the unit is not volt. So let's write it as it is. And we know to find E3 we need delta G3. And delta G3 will be what? Because we have summed equation 1 and equation 2, reverse of equation 1 and equation 2 to get, let's call this as equation 3. This is equation 3. So since you added both of this, you have to add delta G1 and delta G2 to get delta G3. If you had subtracted both of this, in that case you will have to subtract delta G1 and delta G2 to get delta G3. So delta G3 is delta G1 plus delta G2. So if I am going to add them, I'll have 0.153 Faraday plus minus 0.682 Faraday. The answer I get will be minus 0.529 Faraday. Now the question is not complete. We have to find E0 or E30. So E30 will be delta G3 minus delta G3 divided by NF. Okay, so what is minus delta G3? It is minus of minus 0.529 F divided by N. What is the number of electrons involved in the third equation? It's evident it is only one electron. So here N is equal to 1. 1 into F. Now we have two negative signs, cancel them. 2 Faradays, cancel them. What we have left is the E03 value, which will be 0.529. This much volt. This is the E0 value for this particular reaction or the required reaction. And the question was to calculate E0 for that process, and we have done that. So the final answer is 0.529. So I hope that part is clear for you all. Now let's go into a new topic, which will be Nernst equation. To begin with this topic, we need to look into some basics in thermodynamics, which is related to the change in Gibbs free energy. So already from thermodynamics, we know that the relation connecting delta G and the reaction quotient or equilibrium constant. So that was delta G is equal to delta G0 plus RT ln Q, where delta G is change in Gibbs free energy. Delta G0 is again change in Gibbs free energy but at standard conditions. And what was Q? Q is called the reaction quotient. R and T is obviously the universal gas constant and temperature. So if we have a reaction, say A plus B in equilibrium with C plus D. When this reaction has just begun, that means we have just started mixing up A and B. In that situation, it is not actually in equilibrium. Okay, so equilibrium is only attained after a certain time. So during that process, that means before attaining equilibrium, we can write the reaction quotient as Q can be written as concentration of C into concentration of D divided by concentration of A into concentration of B raised to the stoichiometric coefficient if there is any. And especially note that this is or before equilibrium is attained. Now what happens after equilibrium is attained? There is obviously some change in delta G, right? If you remember clearly, we have already discussed that at equilibrium, delta G has to be 0. Delta G will be equal to 0. And one more change is Q, which is your reaction quotient, will change into K equilibrium, or this is called your equilibrium constant. So these are the two changes that we have to introduce into this particular equation when the equilibrium is attained. Okay, so how will we change? Delta G has become 0. So we will write the equation as, let me rewrite this equation before that. Delta G is delta G0 plus RT ln Q. So this is before equilibrium. At equilibrium, we can rewrite it as 0 is equal to delta G0 plus RT ln K equilibrium, which is equilibrium constant. Now what will be delta G0? Delta G0 will be equal to minus RT ln K equilibrium. Okay, this is one important equation, that is at equilibrium your delta G0 will be equal to minus RT ln K equilibrium. Okay. Now how do we formulate Nernst equation from this? So for Nernst equation we will be considering this equation as of now. Okay, so again rewriting that equation, delta G is equal to delta G0 plus RT ln Q. Okay, and we know that delta G is equal to minus NF E cell. And what will be delta G0? Delta G0 will be minus NF E0 cell. Obviously, E cell and E0 cell, they are different. Okay, because E0 cell is dependent only on the nature of the electrode. So for hydrogen electrode, no matter in what condition you take that electrode, the value is always constant. And that value you will be getting from the electrochemical series. If you take magnesium electrode, no matter whatever situations you change, the electrolyte concentration or the pressure or anything, the E0 value will always be a constant. But not so in case of E cell value, it will keep on changing according to the electrolyte solution, the pressure, temperature and all other conditions. Now let's substitute these two into this equation. So I will have, instead of delta G, I can write minus NF E cell. And instead of delta G0, I can write minus NF E0 cell plus what is left? RT ln Q. Okay. Now let's divide throughout the equation by minus NF. Dividing throughout the equation by minus NF. What happens? Here minus NF will be cut, or I'll just rewrite them so there is no confusion. E cell is equal to minus NF E0 cell plus RT ln Q divided by minus NF divided by minus NF divided by minus NF. So here in the numerator and denominator I have minus NF. So in this case also. But here I do not have such common terms. There is nothing to cut. So what is left is E cell is equal to E0 cell plus there should be minus because this minus is to be considered. So let's replace this plus with minus RT by NF ln Q. Okay, so this is one important equation that you have to learn, or this is actually the Nernst equation. E cell is equal to E0 cell minus RT by NF ln Q. Hope all the terms are very familiar to you already. Now, if I consider this under standard conditions, or just if I consider this at 298 Kelvin. Okay, that means I can substitute for the temperature as 298 Kelvin. And Faraday, I already know the value, F is equal to 96500 coulombs. Temperature, already I have told you, I'm considering at 298 Kelvin. And R, we know the value, it is 8.314. Okay. And one more change I'm going to introduce is, I know ln Q is equal to 2.303 log Q. We have learned this in thermodynamics, the relationship between logarithms to the base e and to the base 10. So ln Q will be equal to 2.303 log Q. So by introducing all these three changes into this equation, I can rewrite this equation as E cell is equal to E0 cell minus. So by substituting values, I will have 0.0591 divided by n into log Q. Notice that ln has actually changed into log Q here. Why is that change introduced? Is because only then I will be getting a sufficiently big value to write here. Here you can see I've put a numerical value. So obviously dividing by F, I'm going to have a very small decimal value. So if I multiply with 2.303, which is actually quite big, in that case I'll be getting a sufficiently big value. Even though it is still small, I'll get 0.0591. That is the purpose of using 2.303 there. Okay, so notice that particular change happening from ln to log. So this is also another way of writing Nernst equation. Both are correct, but if it is at 298 Kelvin, this will be an easier one to use. That will save you some time for substituting for R and F. Okay. And if it is not at 298 Kelvin, you should always use this, otherwise your answer is going to be wrong. And both of these equations can be used for full cells as well as half cells. Okay. So we have learned what is Nernst equation. Now let's look into some of the applications of Nernst equation. So the first use is to find the equilibrium constant, that is K equilibrium, of a reaction. So we have just seen from this equation how we can connect E cell and E0 cell, and we already told that delta G will be equal to 0 for an equilibrium reaction. If delta G is 0, what will happen to E cell? Because delta G as you can see here, delta G is equal to minus NF E cell if delta G is equal to 0. We know N cannot be 0 and F cannot be 0. So what will be happening to E cell? That also has to be equal to 0 in an equilibrium reaction. Okay, so this is finding K equilibrium means the reaction should obviously be in equilibrium. So during equilibrium, we know delta G should be equal to 0. Therefore, E cell should also be equal to 0. Now let's rewrite Nernst equation by putting E cell as 0. We know Nernst equation is E cell is equal to E0 cell minus, under standard conditions it is 0.0591, but let's use the general form. That will be RT by NF ln Q. So since it is equilibrium, I will replace Q with K. Q will be equal to K equilibrium and E cell should be 0. So 0 is equal to E0 cell minus RT by NF ln, instead of Q I'll write K equilibrium. Now I can just bring this second term to other side. I will get E0 cell will be equal to RT by NF ln K equilibrium. Since we have to find what is K equilibrium, let's take all the terms to the other side. We will have NF E0 cell divided by RT is equal to ln K equilibrium. Let's take exponential on both sides and just shift the sides. So we will have K equilibrium is equal to E raised to NFE0 cell divided by RT. This is how we will be finding K equilibrium or the equilibrium constant. That is equal to E raised to NFE0 cell by RT. Okay. Now let's move to the second application of Nernst equation, which is to find the solubility product of a sparingly soluble salt. The second one is to find the solubility product. How do we represent solubility product? As KSP. So to find the solubility product of a sparingly soluble salt. So the next question is, what is a sparingly soluble salt? Sparingly means very slightly. So sparingly soluble salt means it is almost insoluble. Only a very small amount is soluble. So only very small amount is soluble. So let's take an example. We have silver chloride. It is a salt of silver metal and chloride non-metal. So if it is undergoing solubility process, what happens? It will be splitting into Ag++ Cl minus, right? Since we already know AgCl is a sparingly soluble salt, so that comes to our mind that only little amount of AgCl would have converted into Ag+ and Cl minus. So if you consider a small beaker where we have taken some water and added some AgCl. Let's differentiate between a soluble and a sparingly soluble salt. So if suppose I add salt like sodium chloride into some water taken in a beaker, all the ions will actually go into the solution. So NaCl will completely dissociate and go into solution like this. Okay. But in case of a sparingly soluble salt, what happens? whatever you add, most of them will be deposited at the bottom like this, and only some of them will go into solution, just this. So majority will be deposited at the bottom. So we say it is sparingly soluble. So if you see that the concentration of AgCl did not change much by giving only some amount of Ag plus and Cl minus into the solution or into the solvent. So after some time of adding the salt into the solution, this system will be in equilibrium. Now if I try to write the equilibrium reaction, it will be looking like this: AgCl in equilibrium with Ag plus and Cl minus. Okay, so if I want to write the equilibrium constant, that is K equilibrium, I know it will be concentration of products divided by concentration of reactants. So from this equation, the concentration of products will be concentration of Ag plus into concentration of Cl minus divided by concentration of AgCl. Okay, this purpose of the second application is to find the solubility product. How do we represent solubility product? As KSP. Now we need to know what is KSP. Okay, so KSP is represented as the product of ions in the solution. Okay, so KSP in general is product of ions in solution. Solubility product KSP is product of concentration of ions in solution. Concentration of ions in solution. All ions should be considered except that of solvent. So KSP in this case will be equal to, what are the ions produced here? Obviously we have added AgCl, so the ions produced will be Ag plus and Cl minus. So this will be concentration of Ag plus into concentration of Cl minus. Now how can we compare K equilibrium and KSP? So one thing you can understand here is, since I already told you that AgCl is not being dissociated much, it is a sparingly soluble salt, so only some amount of the AgCl is dissociated into Ag plus and Cl minus and goes into solution. So we can say that actually there is no much change in the concentration of AgCl. So if the concentration of any entity does not change much, how do we represent it? If concentration of reactant or product, whatever it is, does not change much, or you can say does not change appreciably, in that case we have to consider it as unity. Consider their concentration as unity. Unity means 1. Okay, so we have to consider it as it is equal to 1. So here how do we consider? We consider that concentration of AgCl is equal to 1. So if I consider in that way, what will happen to my K equilibrium and KSP? If AgCl is equal to 1, then K equilibrium will be equal to concentration of Ag plus into concentration of Cl minus. Okay, so if AgCl is equal to 1, my K equilibrium will be equal to concentration of Ag plus into concentration of Cl minus. But already my KSP was also equal to the same value. KSP was also the product of concentration of ions, which means I can consider now that my K equilibrium is equal to KSP, and I can replace, in whichever equations I have K equilibrium, I can replace it with KSP. So just as above, we have found what is the equation for K equilibrium. The same equation I can use for KSP also. which means now I can write E0 cell, this is an equilibrium, so my E cell will be 0. So E0 cell is equal to RT by NF ln, it has to be K equilibrium, but I'm going to replace it with KSP. So I can write it as ln KSP. So what will be KSP? Same as K equilibrium, e raised to NFE0 cell divided by RT. This will be how you can find KSP from the solution or from the E0 value of the solution. The next application that we are going to see is third one. To find the pH of a solution. How can we find the pH of a solution? To understand this better, firstly we need to know what is pH, the formula for pH. So pH, it is equal to minus log concentration of H plus, which means the solution should contain some amount of H plus ions, or at least OH minus ions, and we can find POH and subtract it from 14 to find the pH value. So in general, this means that our electrolyte solution should contain H plus ions. So one system which will contain the H plus ions is obviously the hydrogen electrode. So in order to find the pH of a solution, the electrode which we most usually use is the hydrogen electrode. So now let's try to write the cell reaction of a hydrogen electrode. I can consider hydrogen electrode both as anode and as cathode. So right now let me consider it as cathode and write the cell reaction. So if I consider it as cathode, what will happen at cathode? Reduction happens. So reduction means H plus ions, which is in plus 1 oxidation state, should reduce and become hydrogen gas, which is in 0 oxidation state. So let's write the equation. You will have H plus ions. They have to accept one electron and become H2 gas. So in the right side we have two hydrogen atoms. We need to balance the equation, so let's put a half there. Okay, this is a simple way to balance the equation. I can also put 2H plus 2 electron, but right now I'm considering only for one electron, so I have to put a half H2 there. So this is my cell reaction. Cell reaction if I'm considering hydrogen electrode as cathode. Now I need to write the Nernst equation for this particular cell reaction. How do I write my Nernst equation? Again, the basics, E cell is equal to E0 cell minus RT by NF ln Q. Okay, I'm writing Q because this is not an equilibrium reaction. Okay, so I have already told you that E cell and E0 cell were different. This is not an equilibrium reaction, so E cell will not be equal to 0. Okay, so not equilibrium reaction. So E cell is not equal to 0 and Q is not equal to K equilibrium. Note this. But this is a hydrogen electrode. What is the E0 cell value for a hydrogen electrode? We've already learned it from the electrochemical series, and that we have referenced it as 0 volt. So the E0 value for hydrogen electrode is 0 volt. Now let's rewrite the equation. I will have E cell is equal to E0 cell is 0, so minus RT by NF ln Q. And we know what is Q. Q is concentration of product by concentration of reactant. So I can write E cell is equal to minus, I'm assuming temperature is 298 Kelvin. So at 298 Kelvin, I can write this as 0.0591 divided by N. What is N in this equation? N is equal to 1 electron. So divided by 1 into ln Q. What is Q? Product concentration of product by concentration of reactant. Now I need to see what are the products and reactants here. I will have E cell is equal to minus 0.0591 ln. What is the product? Product is H2 gas. So concentration of H2 gas whole raised to 1 by 2, because the stoichiometric coefficient was 1 by 2, divided by the reactants H plus and an electron. Obviously we are not going to represent the concentration of electrons, so we will take only concentration of H plus. Okay, and one important thing you might be knowing, but I just say it again for you. The concentration of solutions or any species in solution will be taken in molarity or concentration terms itself. Okay, but concentration of gaseous substances, any substance or any species in gaseous form, will be considered as pressure, or we will consider it in terms of pressure. Okay, which means instead of concentration of H plus, I can write this as partial pressure of H2. Sorry, not H plus, it is H2. So instead of considering the concentration of H2 gas, I will consider that as partial pressure or the pressure of H2 gas. Stoichiometry will not change because that comes from the main chemical equation. So this is my equation for that particular cell reaction, the Nernst equation. Now how do we find pH from this? To find pH, I have to do some assumptions or certain corrections here. I need to take that this pressure is always 1 atm, or I have to keep the system such that the pressure at which the hydrogen is being pumped is at 1 atm. I hope you remember the system setup for a hydrogen electrode. It would look something like this. You have a vessel, you have some electrolyte which would obviously contain H plus ions, and the hydrogen electrode. So hydrogen is being bubbled through this, and you will have a platinum wire in here. Okay, this was the hydrogen electrode. You will have electrolyte solutions. Okay, so this pressure, I would take the hydrogen atoms, hydrogen gas pressure as 1 atm. I have to fix it. Only if I fix it, I can find the pH value. Why? Because if the pressure is varying, then I cannot find pH accurately. I need to keep it as 1 atm, and then I have to take. And there is a small mistake. This is not ln. This will not be ln. It has to be log. We've already discussed why. So this has to be log. If I rewrite it by taking pH2 as 1, I shall have E cell is equal to minus 0.0591 log 1 divided by concentration of H plus. Okay, but I know what is log 1 by x. Log 1 by x can be written as minus log x, right? So this one I'll rewrite it as, this can be rewritten as minus of 0.0591 into minus log concentration of H plus, right? This has to be square brackets. Okay, but I again know that minus log concentration of H plus is what? This can be called as your pH value. So I will rewrite this equation as E cell is equal to minus 0.0591 into pH. Now I have got the equation which directly connects my E cell value to the pH of the solution. Remember, this is the equation you have to use only when your hydrogen electrode is used as cathode. Okay. When the cathode is hydrogen electrode, then this is the equation you can use to find pH. What if the hydrogen electrode is used as anode? What are the changes which will happen here? Let's see. So we began by choosing the cathode right here. So if I change it to anode, firstly my cell reaction will reverse. Okay, so cell reaction will become half H2 giving H++ electron. So let's write that also. If I consider my hydrogen electrode as anode, first changes in the cell reaction itself, it will just get reversed. So half H2 will become H++ electron because anode should undergo oxidation. Here you can see from 0 oxidation state to +1 oxidation state, hydrogen electrode is being oxidized. So this is a cell reaction in case of hydrogen electrode acting as anode. Okay, so if this is a cell reaction, what will the change that comes to my Nernst equation? We began the Nernst equation right here. So E cell is equal to minus RT by NF ln Q, no change there. Product by reactant, no change there also. Since the equation is reversed, we can assume that, or we understand that, the reactants would have become the products and the products would have become the reactants when we come from cathode to anode. So the change, or the only change that we have here, is our products would become the reactants and reactants would become the product. So let's exchange those and write. So my E cell value when hydrogen electrode is anode would be minus 0.0591 log product by reactant. Let's write it from this equation itself. What is the product here? It is concentration of H plus divided by, what is the reactant? It is partial pressure of H2 gas raised to 1 by 2. Okay, but I have taken this as 1 atm, which means I can rewrite it as minus 0.0591 log concentration of H plus. Now how to replace it with pH? Already I have minus log concentration of H plus. So instead of that entire thing, I will write pH. Instead of this entire thing, I will write pH. And my final equation will be E cell is equal to 0.0591 pH. What is the visible change here? In the earlier equation, there was a minus sign. That is, when hydrogen electrode was cathode, E cell was minus 0.0591 pH. But when it is anode, there is no negative sign. It is E cell is equal to just plus 0.0591 into pH. So this is the difference when the electrode acts as anode or cathode. Next, let's see what is the fourth application of Nernst equation. So that is connecting with thermodynamic parameters. Thermodynamic parameters. So we have already begun this topic slightly in several places. So this is nothing new for you. So the first thing would be delta G is equal to minus NF E cell. This is the first equation that you have to learn, which connects electrochemistry with thermodynamic parameters. Okay, so we have found for delta G. Now the next two tasks are to find an equation for delta S as well as delta H. So let's try doing that. So in second scenario, we need to find for delta S. So what is the relation connecting delta G and delta S, or dG and ds? We know from the basic equation dG is equal to V dP minus S dt. So if I want to relate G and S, all I have to do is try to cancel out this term. How is that possible? That is possible when dP is 0. So when is dP 0? Change in pressure will be 0 if pressure is a constant. So if I take constant pressure, I will get V dP is equal to 0. Therefore, dG is equal to minus S dt. So if I'm considering large change, I will get dou G by dou T. What is the constant here? Pressure. Dou G by dou T at constant pressure is equal to minus S. Right. Just taking D to this side and converting into partial derivative because pressure was also involved earlier. This is how we have written this equation. We have already seen several times in thermodynamics. We have also seen a graph which represents this equation. Okay, so this is for G and S. If I want to find for delta G and delta S, what can I do? Same equation, just replacing G with delta G and S with delta S. So that will be dou by dou T at constant pressure for delta G. Delta G. I will just replace this with red color one so that you understand the change I have made. And this is equal to minus of S change to delta S. So only change we have introduced is G becomes delta G and S becomes delta S. Now how can I connect delta S and delta G? Delta S and E cell. Just from the above equation we know delta G is minus NF E cell. So instead of this delta G, I am going to put minus NF E cell. So I will have dou divided by dou T of, instead of delta G, minus NF E cell. The whole thing at constant pressure will be equal to minus of delta S. Okay. Now we know that N number of electrons, F Faraday, both are constants which can be taken out of the derivative. So you will be having N minus NF into dou E cell by dou T at constant pressure is equal to minus delta S. There are two minus signs on both sides of the equation. Both can be cancelled. So what is left? NF dou E cell by dou T at constant pressure is equal to delta S. So we have got an equation for delta S also, that is NF dou E cell by dou T at constant pressure. Okay, so this term, that is dou E cell by dou T, is called with a special name, and it is actually called as the temperature coefficient. Okay, so dou E cell by dou T at constant pressure is called temperature coefficient. Now we have found an equation for delta S also, and the third task was to find an equation for delta H. If we have got for delta S and delta G, then finding for delta H is very easy, right? Why? Because we know the third one is for delta H. We know that delta G is equal to delta H minus T delta S. Let's substitute the equations for delta G and delta S. You will directly get an equation for delta H. So delta H is equal to delta G plus T delta S. What is delta G? write it as minus NF E cell plus T into what is delta S? We know it is NF dou E by dou T into NF dou E cell by dou T constant pressure. So in here you see we have NF common. So let's take it outside. So taking NF outside, what is left? You have minus E cell plus T into dou E cell by dou T at constant pressure. So if I write it separately, I will have delta H is equal to NF into T dou E cell by dou T into dou E cell by dou T at constant pressure minus E cell. Okay. So don't be scared about all these equations, because if you know, we already know what is delta G, right? So delta S, something you have to remember, but delta H means the substitution is very easy. If you see, you know delta G and delta S, you can easily substitute and find delta H value. So I would say you don't have to by heart an equation for delta H. Just delta G in equation is something you always use. So you won't be forgetting that. This equation you have to memorize well. And equation for delta S also you have to memorize well. Both these equations you just have to memorize. Delta G is simple one minus NF E cell. Delta S is NF dou E cell by dou T at constant pressure. These two equations, if you know delta H, just you have to know which is this particular equation that you use for substitution. That is delta H is delta G plus T delta S. Okay, so don't memorize this big equation. You don't have to do unwanted memorizations, right? So just understand which is the equation you have to use for substitution and substitute it. So we have learned 4 applications for Nernst equation, that were firstly finding K equilibria, secondly finding KSP, thirdly pH of a solution when hydrogen electrode is used both as cathode as well as anode, and finally connecting with thermodynamic parameters. We have equations connecting E cell with delta G, delta S and delta H.